Welcome back, my friends. Dr. Shaikh here from The Dentalist. We are currently on Chapter 3, the gypsum products for dental casts. In our last video, we learned about the types of gypsum products used in dentistry. Today, we're diving even deeper into the world of gypsum to understand manipulation and setting characteristics. But before we start with the topic, I want to go through the basics of gypsum with you again. I believe you have an idea that gypsum materials are mixed with water to produce a replica from an impression. Gypsum is used in dental offices and laboratories by dentists, hygienists, assistants, and lab technicians. These materials are quite old but still popular due to their ease of use, their affordability, and the long-term stability of the resulting cast model and dies. Gypsum products are generally available as powders that are mixed with water to form a fluid mass or slurry that can be poured and shaped, and that later hardens into a rigid, stable mass. So gypsum is mainly for positive replicas of oral structures. Now here's a question for you, and I want you to answer it in the comments below. If gypsum produces positive replicas of oral structures, which materials produce negative replicas of oral structures? I'll be waiting for your answers. So back to the topic now. These positive replicas are basically called casts, dies, or models, and they are obtained from negative replicas. Now, each replica has a specific purpose. A study model is a kind of replica that is used to plan treatment and to observe the treatment progress. A cast is a replica on which a restoration or appliance is fabricated. A cast is more accurate than a study model and is a replica of more than one tooth, such as a quadrant or a full arch, and it may be partially or completely edentulous. A die is a working replica of a single tooth. Typically, it is a removable part of a cast. Since indirect dental restorations are fabricated on these cast or die replicas, it is essential that we as dental professionals carefully manipulate the gypsum product to ensure an accurate restoration. Now, there are certain properties that we would require from a material for making casts, models, or dies. These properties have been discussed in the last video, but let's quickly do a recap. Because I want this video to be a wholesome for all the gypsum information that I would want to give. So these properties would include accuracy, dimensional stability, ability to produce fine detail, strength and resistance to abrasion, compatibility with the impression material, color, biological safety, ease of use, cost efficiency, and reproducibility. Now we need to understand that not all gypsum products would display all of these ideal properties equally, and this is why different types of gypsum have evolved and exist according to different needs and properties. We've made a separate video about the types of gypsum products used in dentistry, so I would put a link somewhere around the screen for you to check it out after this one. A fun fact to know is that all the gypsum products are made from gypsum rock, which is a mineral found in different parts of the world. The gypsum rock is then converted into powder and then processed to form a range of products. Chemically, gypsum rock is calcium sulfate dihydrate. Remember that, okay? Pure gypsum is basically white, but in most cases it is discolored by impurities. Along with the use of gypsum in various technical fields like engineering, construction, dentistry, medicine, and industries, it is also used in homes in the form of gypsum plaster. So the forms of gypsum products that we use are actually calcium sulfate hemihydrate. They are produced as a result of heating gypsum and driving off part of the water crystallization. This process is called calcination. So what happens is, due to the heat treatment, gypsum loses its water content and turns from calcium sulfate dihydrate into calcium sulfate hemihydrate, releasing water molecules as a reaction to the heat. Plaster and dental stone differ in the physical characteristics of their powder particles as a result of different calcination methods. These differences in powder particles are responsible for their different properties, which make them suitable for various uses. The manufacturers add other chemicals to improve the handling and the properties of the material. So to sum it up, I believe that by now you have understood that gypsum is actually calcium sulfate dihydrate, which comes from a crystallized rock. But gypsum products are processed from gypsum rock by heating or calcination and are converted from calcium sulfate dihydrate to calcium sulfate hemihydrate. And when this calcium sulfate hemihydrate powder is mixed with water, it gradually reaches to a point after mixing or during mixing that it starts forming calcium sulfate dihydrate inside the mix, and it starts crystallizing and hardens up close to its original form. I'm saying close to its original form because the gypsum products contain other impurities as well, like coloring agents, accelerators, retarders, etc., that would not let it convert back to its original gypsum rock form. I hope you get the concept now. So when we talk about manipulation of gypsum, we all should know that the plaster and stone powders are mixed with water to produce a workable mix. The magic begins when the hydration starts, hydration of the calcium sulfate hemihydrate, and it produces the gypsum model or die. I believe you know what gypsum model and die is, as we have discussed before in the video. Now, you need to understand that the mixing of gypsum is critical, and we've got something called the water-powder ratio. This has to be balanced. Here's a logical tip. Always remember that the more water you add with the gypsum powder, the more porous the mix will be. So the water-powder ratio for gypsum should always be 2:1, where we use 2 parts of powder and 1 part of water. This ratio always helps us balance the consistency of the final gypsum product. The tricky part during mixing is when lots of air gets trapped in the mix, leading to surface voids and porosities in the set material. We can get rid of these voids and air porosities by vibrating the mix of plaster or stone on a vibrator in order to bring the air bubbles to the surface, and by mixing it mechanically. When mixing by hand, cleanliness is the key. A clean, scratch-free rubber bowl and a clean, dry spatula are normally recommended. The presence of gypsum residues in the mixing bowl can noticeably alter the working and setting characteristics of a fresh mix, and so the need for cleanliness is extremely important. Don't compromise on that. The requisite amount of water is added first to a moist bowl, and then powder is added slowly to the water over about 10 seconds. The mix is allowed to soak for about another 20 seconds, and then mixing is carried out for around 60 seconds using a circular stirring motion in a single direction. A lot of people put the powder in the bowl first and then add water accordingly. You can do that too, but the preferred method would always be the one that I told you first. After the material has been mixed and used, the mixing bowl should be thoroughly cleaned before the next mix. I repeat that again, okay? The fluidity of dental gypsum products is normally measured by one of 2 methods: slump test or core penetration test. For types 1 and 2 materials, slump test is recommended. Now, how the slump test works is that a known volume of mixed material is allowed to slump onto a glass slab at a time indicated by the manufacturer as pouring time, which is usually 2 to 3 minutes for most gypsum materials. The fluidity is defined as the average of the major and minor diameters of the slumped material. It is basically the flow of gypsum material when being transferred from the rubber bowl to the mold after the mixing phase. The fluidity of types 3, 4, and 5 materials is determined using a core penetration test. The depth of penetration is measured 3 minutes after starting to mix powder and water. This depth of penetration of a core is measured by putting a load for every 15 seconds into a known quantity of material to find out the fluidity and the initial and final setting times. The apparatus used to measure the depth of penetration of gypsum is called Gillmore apparatus. The needles used are called Gillmore Needles. So sometimes people call it Gillmore Needle apparatus. The setting process begins rapidly after mixing the powder and water. The first stage in the process is that the water becomes saturated with hemihydrate, which has a solubility of around 0.8% at room temperature. The dissolved hemihydrate is then rapidly converted to dihydrate, which has a much lower solubility of around 0.2%. That means it does not get dissolved in water. Since the solubility limit of the dihydrate is immediately changed, it begins to crystallize out of solution. The process continues until most of the hemihydrate is converted to dihydrate. The crystals of dihydrate are spherulitic in nature and grow from specific sites called nuclei of crystallization. These may be small particles of impurity such as unconverted gypsum crystals within the hemihydrate powder. If a thin mix of a material is used containing more water than that indicated, the formation of supersaturated solution of dihydrate is delayed. As we discussed before, the formation of supersaturated solution of dihydrate is actually responsible for crystallization. Therefore, when there's more water in the mix, there's less saturation of dihydrate, and thus the centers of crystallization nuclei are more widely dispersed by the dilution effect. Imagine that. And then the set plaster is therefore less dense with greater spaces between crystals, leading to a significant reduction in strength. If you have worked with gypsum products, you know that the material should be used as soon as possible after mixing, since its viscosity increases to the stage where the material is unworkable within a few minutes. During setting of gypsum, 2 stages can be identified. The first is the time at which the material develops the properties of a weak solid and will not flow readily. At this time, it is possible to carve away the excess material with a knife. The materials continue to develop strength for some time after initial setting and eventually reach a stage when the models or dies are strong and hard enough to be worked upon. The time taken to reach this stage is referred to as the final setting time, although this term is misleading since it implies that the material has reached its ultimate strength. However, its ultimate strength may not be reached until several hours after mixing. The setting characteristics of gypsum products can be affected not only by the presence of unconverted dihydrate but also by the presence of anhydrite, the age of the material, and the storage conditions experienced by the material prior to use. Small quantities of unconverted dihydrate act as centers for nucleation, as we discussed earlier. Anhydrite reacts very rapidly with water, producing a marked acceleration in setting. Just to let you know, anhydrite is the form of gypsum that does not have water, so it's only calcium sulfate. That's it, without hemihydrate or dihydrate. Freshly produced plaster may contain significant quantities of anhydrite, and this may accelerate setting to the extent that manipulation becomes difficult. To overcome this problem, plaster is often allowed to mature before use. The anhydrite absorbs moisture and is converted to the less reactive hemihydrate with time. If the plaster is allowed to mature for too long in a humid environment, the hemihydrate crystals become coated with a layer of dihydrate, and the reactivity is markedly reduced. The setting characteristics of gypsum products have traditionally been measured in terms of their ability to resist penetration by needles, as we discussed before. Remember the Gillmore needles? The heavier needle has a smaller tip diameter than the lighter one, and hence applies a considerably greater pressure to the surface of the material under test. The initial setting time is defined as the time taken for the material to develop sufficient strength such that it is able to support the lighter of the needles. The time at which the material is able to support the heavier needle has doubtful practical significance, since it indicates a time somewhere between the initial and final setting times, and is not indicative of the fact that the model or die is hard enough to be used. So the ISO specification for dental gypsum products requires the use of a Vicat needle for judging setting time. This system has a built-in dial gauge, allowing depth of penetration to be measured. Setting material is indented by a needle of 1 millimeter diameter under a load of 300 grams. The setting time in this test is defined rather arbitrarily as the time when the needle is no longer able to penetrate to a depth of 2 millimeters into the material. The setting time measured using this method is normally less than 30 minutes. However, a longer time is required before the material has matured sufficiently to allow any further work to be performed on the cast without damaging the surface. Now remember, the setting reaction for gypsum is exothermic. That means the maximum temperature is being reached during the stage when final hardening occurs. It is interesting to note that the temperature rise is still negligible at the time of the initial set. The magnitude of the temperature rise depends on the bulk of the material and can be as great as 30 degrees at the center of a mass of the setting material. This temperature may be maintained for several minutes due to the thermal insulating characteristics of the material. Now, this marked rise in temperature can be used to good effect when flasking dentures, since it softens the wax of the trial denture and enables it to be easily removed from the mold. Another physical change which accompanies setting is a small expansion caused by the outward thrust of the growing crystals. The maximum rate of expansion occurs at the time when the temperature is increasing most rapidly. The expansion is, in fact, only apparent since the set material contains a considerable volume of porosity. So if the material is placed in water at the initial set stage, considerably more expansion would occur during setting. This increased expansion is called hygroscopic expansion and is sometimes used to increase the setting expansion of gypsum bonded investment materials. We'll discuss about gypsum bonded investment materials in detail later, and we'll understand more about hygroscopic expansion, but I believe you now have a basic idea about what hygroscopic expansion is. It is simply the expansion that occurs when the plaster is placed in water at the initial set stage. Now, you must be thinking, how would we measure the setting expansion? The setting expansion is measured using a special trough with a movable end plate which pushes against an extensometer. Mixed material is poured into the trough, and as it solidifies and expands, the extensometer is displaced, giving a value of linear expansion. Factors which control the setting times of gypsum products can be divided into those controlled by the manufacturers and those controlled by the operator. The manufacturer can control the concentration of the nucleating agents in the hemihydrate powder. A higher concentration of nucleating agent produced by aging or from unconverted calcium sulfate dihydrate results in more rapid crystallization. Also, the manufacturers may add chemical accelerators or retarders to dental stones. Potassium sulfate is a commonly used accelerator which is thought to act by increasing the solubility of the hemihydrate. So what happens when the solubility of the hemihydrate increases? You tell me in the comments. Now moving on, borax is the most widely used retarder, although the process by which it works is not clear. Factors under the control of the operator are 3 in number. Surprisingly, temperature variation has little effect on the setting times of gypsum products. This is due to the fact that the setting involves a dissolution of one sparingly soluble salt, which is calcium sulfate hemihydrate, followed by crystallization of another, which is calcium sulfate dihydrate. Increasing the temperature accelerates the solution process but retards the crystallization. Thus, the two effects tend to cancel out. Increasing the water powder ratio retards setting by decreasing the concentration of crystallization nuclei. Increasing mixing time has the opposite effect. This accelerates setting by breaking up dihydrate crystals into more nuclei and more crystals during the early stages of setting. Now, in order to produce an accurate model or die, it is necessary to maintain the setting expansion at as low a value as possible. Accelerators or retarders which are added by manufacturers to dental stones in order to control the setting time also have the effect of reducing the setting expansion and are sometimes referred to as anti-expansion agents. You should also know that alterations in water powder ratio and mixing time have only a minimal effect on setting expansion. Now, let's discuss the properties of gypsum after it sets. The strength of gypsum depends primarily on the porosity of the set material and the time for which the material is allowed to dry out after setting. The porosity and hence the strength is proportional to the water powder ratio. Since stone is always mixed at a lower water powder ratio than plaster, it is always less porous and consequently much stronger and harder. Although a gypsum model or die may appear completely set within a relatively short period, but its strength increases significantly if it is allowed to stand for a few hours. The increase in strength is a function of the loss of excess water by evaporation. It is thought that evaporation of water causes a precipitation of any dissolved dihydrate and that this effectively cements together the crystals of gypsum formed during setting. So, if you let your model or die dry out for a few hours before starting to work on it, you will have much better strength. Despite precautions which may be taken to ensure optimum mechanical properties, gypsum is still a very brittle material. The very low value of flexural strength of plaster is indicative of how fragile this material is. Do you remember what flexural strength is? I know you need to recall. Feel free to watch this video to know what flexural strength is after you finish this one. Okay? Now, here's a fact. Dental stone is less fragile, but it must be treated with care if fracture is to be avoided. It is relatively rigid but has a poor impact strength and is likely to fracture if dropped. We've talked about impact strength in our previous videos, so I'll put a link somewhere on the screen so you can go and check it. Attempts to improve the mechanical properties have involved the impregnation by a polymer such as acrylic resin and the use of wetting agents which enable the materials to be used at a lower water powder ratio. The dimensional stability of gypsum is good. Following setting, further changes in dimensions are immeasurable and the materials are sufficiently rigid to resist deformations when work is being carried out upon them. The ability of dental gypsum products to reproduce surface details of hard or soft tissues, either directly or from impressions, is central to their suitability as model and die materials. This ability is judged by measuring the extent to which accurately machined lines in a block of stainless steel can be reproduced in a sample of the material, as in the gypsum material is poured over a block of stainless steel that has fine grooves or lines engraved on it. Types 1 and 2 materials can reproduce a groove 75 micrometers wide, while types 3, 4, and 5 are able to produce grooves of 50 micrometer width. Hence, the types 3, 4, and 5 stones are capable of recording greater fine detail than type 2 plaster. Set plaster is slightly soluble in water. Solubility increases with the temperature of the water, and if hot water is poured over the surface of a plaster cast, as happens during the boiling of a denture mold during flasking procedure while working at a prosthodontic lab, a portion of the surface layer becomes dissolved, leaving the surface roughened. Frequent washing of the surface with hot water should therefore be avoided. Now, for applications of dental gypsum, it really depends on the nature of work that is required from the material. When strength, hardness, and accuracy are required, dental stones are normally used in preference to the dental plaster. The stone materials are less likely to be damaged during the laying down and carving of a wax pattern and give optimal dimensional accuracy. Thus, these materials are used when any work is to be carried out on the model or die, as would be the case when constructing a denture on a model or a cast. When mechanical properties and accuracy are not of primary importance, the cheaper dental plaster is used. Thus, plaster is often used for mounting stone models onto articulators and sometimes for preparing study models. Gypsum model and die materials have the advantages of being inexpensive and easy to use. The accuracy and dimensional stability are good, and they're able to reproduce fine detail from the impression, provided that the precautions are taken to prevent the blowholes. The mechanical properties are not ideal, and the brittle nature of gypsum occasionally leads to fracture, particularly through the teeth, which forms the weakest part of any model. Problems occasionally arise when gypsum model and die materials are used in conjunction with alginate impression. The surface of the model may remain relatively soft due to an apparent retarding effect which hydrocolloids have on the setting of gypsum products. It is not certain whether the retarding effect is due to borax in the hydrocolloid or due to the absorption of hydrocolloid into the gypsum crystals, which act as nuclei of crystallization. Despite these observations, it cannot be said that gypsum products are incompatible with alginate impression materials, since problems arise very infrequently. Alternative materials for the production of models and dies exist, but are hardly ever used. These include various resins, cements, and dental amalgam. The alternatives may be stronger, but are generally less stable, difficult to use, and more expensive. The surface of a gypsum die can be hardened by electroplating the impression prior to constructing the die. The thin layer of metal, copper for impression compound, and silver for some elastomers is transferred to the surface of the die on separation from the impression. Another treatment which has been suggested for improving the durability of gypsum is to partly saturate the set material in a polymerizable monomer, which is methyl methacrylate or styrene. Polymerization of the monomer produces a polymer phase, which occupies many of the porosities in the set gypsum and increases its strength and toughness. Despite these apparent advantages, these techniques are rarely used in practice. Who has time to use all these? That is all for today, my friends. I hope this video would help you in understanding the concepts of dental gypsum, which is a very important material used in dentistry. And since it is a very important material, I have tried to cover everything in one video for you, so you don't have to look for anything else regarding dental plaster. If you found this helpful, please like and share this video and subscribe to the channel if you still haven't. Also, please feel free to provide your feedback on this video and write down your questions if you have any. I will see you in the next one. Take care till we meet again.